Okay, what I'd like to do is use Desmos to try to walk us through a very common type of problem where they give us a derivative and they give us a function value, and then they ask for a table of values, and then they ask for a really good graph. This is going to take a while. We're going to take our time and to see what we can go through. Remember, they're telling us that this is the derivative of big F, and they also gave us a single function value. They told us that the function value there was 3. So I'm going to put it in like that, and we have a function value. That's awesome. Now, how am I supposed to find the other function values? Well, using the fundamental theorem of calculus. So what we're supposed to do is go from left to right and start accumulating areas as we go. Um, there are a number of important points that are essential to include, and we really shouldn't have to do anything besides those. But which ones are essential? Well, any place where the derivative, which is what's graphed here, is 0. Well, that happens at 1.5, that happens at 3, that happens at 7, that happens in 10. I absolutely want to include all those. Where else do I want to include? Any place where the derivative starts increasing or decreasing corresponds to where the original function changes concavity. So, oh boy, do I want those points. So, for example, 1 is very important because the derivative starts to decrease there. 2 is also going to be important. 5 is going to be important. 7.5 is going to be important. 9 is going to be important. And 10 is going to be important. So I want to make sure I put all those x values into my table, and we'll try to walk our way through it. So 1's important, 1.5 is important, 2's important, 3's important, 5's important, 7's important, 7.5 is important, 8 is important, 9 is important, and 10. Now, how does this work? They gave us the single function value, and we're supposed to use the fundamental theorem of calculus to get all of the others. Well, how am I supposed to get the value right in this spot right here? Well, what I'm supposed to do is I'm supposed to say, if you want, why don't we just use distance traveled so we can do this, right? If I want the distance traveled by 1 o'clock, I need to know where I was at 0 o'clock plus how far I traveled, which is the area under the rate graph. So I'm going to go up here. I'm probably going to get in trouble. I want to turn on the inequalities, that shades. No, it doesn't want to do that for me today. There we go. That's shading too much. I don't want to go all the shading. I just want to go from 0 to 1. So I'm going to take my little inequality, and I'm going to go like this, and put a 1. That's how much area I want to add. So I'm going to come down to my table, and if I want to know where I was at 1 o'clock, I need to know where I was at the very beginning, which is 3, plus the distance traveled, which is the area under the rate graph, and that's that. So I actually get to the point 4. I'm going to leave it as 3 plus 1 for the moment. Now, what am I supposed to do? I'm supposed to accumulate more area, starting where I'm at, and ending up at the next important point. Let me come over here. I want to start at 1, and I want to go to 1.5. So you can see that little shading there. Now, what am I supposed to do? If I want to know where I was at 1:30, I need to know where I was at 1 o'clock, which was height 4 or 4-mile marker, or however you want to do it. Yes. Plus the area of that triangle. Well, the height of the triangle is 1, the width of the triangle is 1/2, the area of the whole triangle would only be 1/4. So we're not going up a whole lot. The next thing I want to do is go from this point at 1.5 to the next important point, which is 2, but you can see there I'm actually taking down area. So what I want to do is stop accumulating there. I don't know why it keeps doing this to me, but it does, and it's going to do it again. Here we go. Oh, it did. That's too much shading. I don't want to shade all that. I want to shade just the stuff between 1.5 and 2. So I'm going to put a little inequality here, like this. There we go. Now, remember, that's area under the graph. This is signed area. If this is the velocity graph, this blue area here represents distance we went down. So if we're thinking of this in terms of height, if I want to know my height at 2 o'clock, I needed to know my height at 1:30, which is 4.25, minus the area I have right here. Well, the area of that's also 1/4, and so we get that. So we're back down to 4, I think. Now what we're supposed to do is from this point to this point, we're decumulating more area. Let's just shade it so you can see it. I want, what do I want? I want between, I think 2 and 3. Let's try that. 2 is less than x is less than 3. How's that? Yeah, there it is. Now, the area of that is a half, right? Because this is 1 by 1. All right, so what I'm going to do is, I'm now thinking in terms of height. I guess I settled on that. If I want to know my height at 3 o'clock, I need to know my height at 2, which is 4. And then the area of this is a half, but it's under the graph, so that means we went down. So I'm going to do that and get minus a half, like that. Yay. All right. Now the next thing I'm supposed to do is go from one important point to the next important point. 3 is an important point, 5 is an important point, so I want to shade that much from 3 to 5, just so you can see it. I'm going to try to shut this part off, and it just is making me do this twice today. I haven't figured out why. I want to turn this one on, but I don't want there. I want to go from 3 to 5. So let's go put a little 5 right there, and put a little 3 right there, and hey, there's the area I want. Now, this is the top half of a circle. This is, by the way, taken from a Wiley Plus problem, but or the book, actually. But anyways, you can see this is a circle. It is a circle of radius 2, so the whole circle would be area of 4 pi, but this is just a quarter of that, so that area is exactly pi. So I'm going to go over here, and I'm going to say if I want my height at 5 o'clock, I need my height at 3 o'clock, which is 3.5, plus how much area I accumulated. I'm going to put a little pi like that, and I got that much. The next important point is 7. If you want to see how much area we're going to be shading, we're going to go between 5 and 7, so that's that much area. This half was pi, this half is pi, so between 5 and 7 o'clock, I'm adding another pi, so this is going to be, what I was going to have here, we're going to have 3.5 plus pi, plus another pi, like that, and that's going to give us another value. This should represent how high we are at 5. Looks like almost 10, but we'll get there. The next thing I want to do is go from this important point, which is 7, to the next important point, which is 7.5. But I'm again decumulating. So I'm going to come over here. I'm going to try to shut this off, and it's going to say no. I'm going to go back up here. I'm going to try to shut this off again. And now it says yes. I'm so happy with that. I don't want to shade that much. I want to shade the part between 7 and 7.5 so we can see it. Now each of these squares is a quarter, and I can see here then that what I have is a half. I think that's right. So I'm going down a half. All right, here we go. So if I want to know how high I'm at 7:30, I need to take my height at 7, which was 3.5 plus 2 pi, and then subtract a half, like that. Yay! All right, now I need to go from one important point to the next important point. 7.5 was important because that's where we stopped, where the derivative stopped decreasing. I now want to go to 9 because that's where the derivative starts increasing. So I want to shade everything, I think, between 7.5 and 9. And I think the only problem I'm going to have with this is actually calculating the area. I wish you were here so you could help me. This is very easy to get wrong. I'm going to try counting squares, thinking each square is a quarter. Let's see, if each square is a quarter, right? Which I think that's right. I see 9 quarters. Does that sound right? Let's try this again. This is going to be 3 quarters times 2. That's 3 halves. 3 halves. Yep, I think that's right. So we're going to subtract 1.5. I think that's right. We're going to see. Oh, okay. If I want to know my height at 8, I want to know my height at 7:30, which was 3 plus 2 pi. And I'm going to subtract 1.5, I think. Does that sound right? Going to subtract 1.5. Let's see, I'm being too hyper here, but it doesn't sound right. Let's see here. This goes over 1. It goes down 2. That's 2. I think that's 3. Okay, I'm going to subtract 3, and we'll check it later. Great. Anyways, now from 8 to 9, we're still going down because this is area under the graph. If you want to see how much we're going down, I'll try to get this to shade this again. It should be between 9 and 10. like that. That's good. Now each thing is a quarter, right? So if each one's a quarter, this whole thing would be 8 quarters. The whole thing would be 2. So I think it's just 1 again. Well, I'm going to pretend it's 1 and we'll just see what happens. Never should have included 8. That's the problem. All right. 8 was not an important point. There we go. We're going to get rid of this one. There, I feel so much better. All right. At 10, what am I supposed to do? If I want to know how my height at 10 o'clock, I need to take my height at 9 o'clock, which was 2 pi. And I'm supposed to subtract, what did I say that was going to be? Minus 1. So I'm going to say minus 1. Right? And I think that's supposed to be right. Yep, we're going to see. All right, so what we get is a bunch of points that are supposed to be the most important points to find on the original function. If I try plotting the points, I'm just going to put in the points like that. Well, let me do this to it. It will. There we go. And it looks to me like what we have is something that goes up like this, and over like this, and down like this, and up like this, and up like this, and then down and down and down like this. Somewhere here, I think I have a formula, and you can see that's actually the right graph. The concavity is very important, by the way, and I want to talk about that just for a second. When the derivative is constant, the original function is linear. When the derivative is decreasing, the original function is concave down. When the derivative is decreasing, the original function is concave down. When the derivative is increasing, the original function is concave up. When the derivative is increasing, the original function is concave up. Remember, this is the graph of the derivative here. When the derivative is decreasing, the original function is concave down. When the derivative is decreasing, the original function is concave down. When the derivative is constant, the function is linear. And finally, when the derivative is increasing, the original function is concave up. So you can see how we get the graph. We use the Fundamental Theorem of Calculus at just about every point. We got all the important points. In practice, I would like to see some sentences, but Desmos won't let me write any more sentences. So I apologize for that. But at least we've walked our way through one of these problems.